Welcome to solverfy.
6.55. So the rings of Saturn are made up of chunks of ice and stuff that sort of orbit around it. The rings aren't like some sort of solid object that spins around Saturn. They're a collection of these little chunks. Now the inner radius of the ring or rings is 73,000 kilometers, and then the outer radius is 170,000 kilometers. And so we want to find what the period of one of these chunks of ice is at this inner radius and at the outer radius, and then compare it with Saturn's rotation period, or the length of its day of about 10.5 hours. So to find the orbital period of something, we can start off by using two expressions for what its speed has to be. One is based on the sort of considerations from Newton's law that we've seen, and then also one just from purely the what speed is and the geometry of a circular orbit. It has to be moving the circumference of the orbit in the amount of time it takes for that orbit to occur. So that's what the period is, and then that's the 2 pi r is the circumference. And so from this we can get Kepler's period and distance law in a form with the actual proportionality constant given. So 4 pi squared over gm times r cubed. And so now the period is 2 pi times the square root of r cubed over gm. We're told that the mass of Saturn is 5.7 times 10 to the 26th kilograms, which is quite large, which you would sort of expect for a gigantic planet, which Saturn is quite large. So then putting in the inner radius, we find that something on the, if here's Saturn, and then here's its rings for some point sort of at the inside of the rings. This period is 2 times 10 to the 4th seconds. And then at the outside here, it's 7.1 times 10 to the 4th seconds. And then the length of a day, or the rotational period on Saturn, it tells us that it's 10 hours and 39 minutes, but these are in seconds, and so let's convert that to seconds. And we find that that's about 3.8 times 10 to the 4th seconds. And so, if you were somewhere on Jupiter, then if you could make out an object at the inside of the rings, it would sort of move across the sky faster than the sun. And if you could make out an object on the sort of outside of the rings, it would move slower. But in both cases, it's pretty comparable, so it would sort of be a subtle effect. Well, I mean, this is almost twice as long, but still, it's fairly subtle. Um, how exactly you would make out a difference between the two. I guess if you're somewhere sort of above, at like a higher latitude on Saturn, you might be able to see the rings because, or not see the rings, but see the actual like width of the rings. Because like if you were here and here's the rings, then good luck distinguishing objects here versus here. But if you're up at a higher latitude, then you sort of could have a full view of them.